Okay, we'll go ahead and get started. My name is Jeff Wright. I'm the CITRIS co-director at the Merced campus. Welcome to our special seminar today, and I extend a welcome to our distance viewing audience as well. A couple of announcements before we get started. Next week, spring break, we will not have Research Exchange or I4E seminars. I want to remind you, however, that the Big Ideas poster presentations are scheduled for the 14th of April. They'll be out here in the atrium. Please plan to attend. I looked over the list that Yvette gave me of the entrants, and we've got a tough job selecting the winners. We've got some fantastic entrants this year, so please join us on April 14th for the Big Ideas posters. Let me remind you also that the composting program is in full swing. Make sure that if you have tinfoil, that goes into a separate bin, as well as the plastic bottles and cookie bags, but everything else can go into the compost bin. So I'm very happy to introduce our speaker today, Ed Seidel, currently Assistant Director for Mathematical and Physical Sciences at the National Science Foundation. Prior to that, he was director of the NSF Office of Cyberinfrastructure. Before going to NSF, Ed was the founding director of the LSU Center for Computation and Technology, where he continues to hold the position of Floating Point Systems Professor Chair in that unit. Ed holds a PhD in astrophysics from Yale University. He was formerly with the Albert Einstein Institute in Potsdam, and also worked as a research scientist and professor at NCSA, the National Center for Supercomputing Applications at University of Illinois in Champaign-Urbana. His numerous research awards include the Sidney Fernbach Award, the Heinz Billing Prize of the Max Planck Institute, and the Gordon Bell Prize. His talk today is titled The Data and Compute-Driven Transformation of Modern Science. Please welcome Professor Edward Seidel.
Thanks a lot. Thanks very much. It's great to be back here in Berkeley, although I'm only here for about 24 hours, sadly, as usual. But I wanted to tell you specifically today about not only how important computing and data are, but also the view that I'm increasingly picking up from the National Science Foundation about how transformational it all is and how it impacts every area of not only science or engineering, but also of research, and of course going right on into society very rapidly. And in many cases, I think scientists are used to sort of leading the wave of innovation, but I think a lot of this is now coming more on the societal side, and that we're going to be dragged along, in fact, in many areas. And so I'll kind of hint at those things as we go forward. I guess I have a number of illustrations here to start off. First of all, on the left-hand side here is just an image of a calculation of a supernova that has many levels of adaptive mesh refinement. You can barely see them here, but some work carried out by a team of people led by Christian Ott at Caltech. But the important point is, and I'll get into this in a little bit more depth as we go forward, but many different groups need to contribute some kind of expertise in order to look at the problem of a supernova or ultimately something like a gamma ray burst, from computer science to many subdisciplines of physics and astronomy, and you need them all in order to attack that problem. So a lot of my talk today is really about the culture change that's needed in order to allow that kind of investigation to really take place. The middle image there is a simulation of gravitational waves from colliding black holes, some work from my old research group. But if you look at the magazine that it's not on Physical Review, but Communications of the ACM, this says Blueprint for the Future of High Performance Networking. So it's an example, in this case, of where science is really driving the technologies that are needed, and high-performance networking is going to be absolutely critical as we start dealing with the kind of data volumes that we're talking about, and I'll get into that. In fact, I read just in the last year, I think the U.S. mobile phone traffic has actually generated an exabyte of data that's been transmitted to mobile devices. So talking about exascale computing, it's already happening at the level of distributed systems that we all have in our pockets. And then on the right-hand side is a picture of the LIGO facility, the Laser Interferometric Gravitational Wave Observatory, which is about to detect in the next few years, we expect gravitational waves. And I'll get into this, but one of the key points is that all of these three examples actually are very related to my own scientific discipline, which is general relativity, a discipline that's been dominated over most of the history of the field by singular individuals like Einstein, who would do work more or less in isolation, but working with an apprentice of a student or two, and then carrying on work in a certain style. And now every single area of that field is being revolutionized in a major way by computing, and it's becoming very highly data intensive. And so just that's an idea to really carry home. That is, even areas that have been not very data intensive, not very compute intensive over their histories are now becoming drivers for that. So the first, have this talk broken up into a number of parts. The first one is just about the changing culture of science and the methodologies and the changing methodologies and the crises they're creating. They're creating a number of crises for us. And I have few solutions, but I just want to illustrate how everything is growing, in some sense, out of control, and we need to find a way to control it, or not control it, but to live with it and to use it to our advantage. So I wanted to start then with a little history lesson, the history of science, starting from the point of view of a gravitational physicist. So our first real understanding of gravity came about 400 years ago with people like Galileo and Newton. And I want to just point out the way they worked. I'm not going to talk so much about the science itself, but more about the culture. So they had a particular problem they were looking at, a single particle in a gravitational field. If you go up to two particles in a gravitational field that are fully self-gravitating, that's been almost impossible to solve for over the centuries, and only very recently through computational means have we been able to do that. But so that was the problem. The kind of methods that they used were, they were taking data, understanding the solar system, and looking at the motions of the planets and trying to figure out from that, what is a theory of gravity? So it was a data-driven science from that point of view. And they would collect data in notebooks, and if you were to digitize that, you would find it's of order kilobytes of data. Okay? The theory was driven by data. Computation was important, so Newton in particular even invented a new form of mathematics, could carry out computations. If you were to imagine how many floating point operations a brilliant scientist could do in his head or on paper, it's probably about one floating point operation per second, I would say, something like that. That's pretty good. And so the collaboration, the style of collaboration was a brilliant scientist with an apprentice, and then sort of passed down very slowly over the ages. The knowledge was passed down in that way. So that's what it used to be like. And that's actually what it's still like, almost. And so just a few decades ago, I come to a sort of modern version of the same kinds of figures, Stephen Hawking, now looking at the problem of two bodies, not just one, but two, in this case, black holes, and working out the structure of event horizons as they collide, as two black holes collide. So this is time going up, and this is space, and in this case, two black holes come together, and they collide and form a big black hole. This is worked out by a single person doing a scientific visualization. And if you were to then digitize this, you'd find that it's probably 50 kilobytes of data, something like that, I just estimate. And so my main point is that almost 400 years later, the culture of doing science didn't change very much. And this is our modern day, right? So this is really, most of us who are my age and up have been trained in this sort of style of science. But this is increasingly the trend that we have, and it's changing really dramatically. So about 20 years later, a group that I was involved in fact, and a member of our group was out there in the audience who helped do this visualization, in fact, this allowed us to do this calculation on a supercomputer. So rather than working out just the theoretical aspects, working out, solving Einstein's equations as a set of PDEs, and then seeing what happens when two black holes collide, including in detail where the photons on the generators of the horizon go, what happens to the gravitational waves that might be generated, that propagate out, and so on. But you see there's a transition in the terms of the type of problem this is, because it involves visualization, it involves parallel algorithms, it involves data analysis, mathematical algorithms, as well as the basic physics of general relativity, and nobody can know all of that. So you need to bring together teams to figure out how to do this. And so the point is, in just about a couple of decades, you've moved from 50 kilobytes to 50 megabytes. That's the kind of data generated at that time. That's a factor of 1,000. Now, just go on one more step forward to a full three-dimensional version of this problem, two black holes colliding. And just a few years later, we were able to go to full 3D, and we had a group of about 15 people with a much larger computer. In fact, this is a 256 processor computer. This is a 4-processor computer, an old Cray 2 or Cray YMP. This was a 256 processor SGI Origin 2000, a much larger group, and the data volume's 50 gigabytes. So another factor of 1,000 in data in just a few more years. So now, this is the modern day. We now have teams of people in this field that's used to, over its entire history of hundreds of years, working as single members, more or less in isolation. We're now developing community toolkits that are very complicated. So I'll show you a movie of two black holes colliding now, carried out by a collaboration centered at the Albert Einstein Institute in Potsdam, where I used to work. But the point is that this toolkit now has a consortium of 55 members across 9 countries. And it's become an endeavor in software engineering, where people have to learn how to develop modules that fit together, in sharing of data and software, and then the knowledge that those encapsulate. So there's a sharing requirement there for these collaborations to work together, and so on. So let me show you the visualization. So this is an adaptive mesh simulation of two black holes colliding. So we're zooming in through the different meshes, and this is where all the action is. The black holes are actually way down here, something like 10 levels of mesh refinement. And then you get to the black holes. And so this Einstein's equations, if you're not familiar with them, are a very complex set of PDEs with many thousands of terms. So there's a huge amount of arithmetic that has to be carried out at every single point on this grid. And then we'll show the evolution of this system going forward in time. That shows what would happen if two black holes that were in orbit around each other, so two stars as a binary pair, each had collapsed to a black hole, but they're still going around. And as they circle around, they emit gravitational radiation, which has been predicted by Einstein but never yet observed. And then as they lose their energy, they begin to spiral in and they coalesce and then they form a large black hole. So the simulation will start just right here. So in this visualization then, which is then carried out by a separate group working in concert with the group in Potsdam, you see the gravitational wave field here as the colors, and the two black holes. These are spinning black holes now, so they can now do simulations that have arbitrary orientations of spin of the black holes. They'll coalesce, and boom, a big black hole forms. The gravitational waves come out. And so this is a problem that is of great interest in astrophysics right now, because we've never seen gravitational waves. They've been predicted by Einstein since around 1918 or so, but they've never been seen. And so we're looking at very strong cosmic sources of things, like, for example, colliding black holes or neutron stars, really violent events in the universe. And so these are the kinds of sources that we expect to see when the gravitational wave detectors reach the sensitivity that will allow us to verify Einstein's equations and his theory, but also to tell us if we see those signals, what did they come from? Is it two black holes, or does it prove the existence of black holes? Does it tell us something about the nuclear equation of state inside a neutron star? And so on. So we'll be able to do diagnostics from these observations and really understand much more about the universe. So now, after many years, so I spent most of my career not doing many orbits, as you saw there, if you watched that those two black holes went around each other many times. So nowadays, that's like a test problem. But for my entire career, it was, could we actually get black holes to even do half an orbit before something would go wrong with the computer simulation? Because we didn't understand enough about the numerics, or the way to write the hyperbolic system, or the way to do the computations on adaptive meshes, etc. Now this has become routine through collaborative endeavors, and there are many, many groups around the world that can do this. And so now, in effect, Einstein's equations are now solved. After a century of not being able to solve them, we can solve them in fairly routine, three-dimensional versions without having to worry about making specific simplifications of them. So we'd like to be able to detect the waves that then are predicted, and we haven't yet done that. So right now, the National Science Foundation has a project called LIGO, Laser Interferometric Gravitational Wave Observatory, and we have two detectors. And what they do is unbelievable. So you have these detectors that have laser beams bouncing back and forth inside between mirrors in a vacuum tube, and another one coming this way. And when two black holes collide somewhere over there, they'll emit gravitational waves. And what happens when a gravitational wave passes through you, so I'm emitting them right now, and you are being affected by them. And what happens is they stretch and squeeze the spatial dimensions of your body. So you will feel slight, you won't feel it because it's too slight, but you will actually oscillate in certain ways. And what happens when they hit these detectors is that the path length will be squeezed, the distance between these detectors will be squeezed, and the path length changes while it stretches here. And so when you allow these laser beams to interfere, then when the path length changes, the interference pattern will change, and from that you can infer gravitational waves. Now, it's incredible to think that the amount that these detectors will actually vibrate is something like, it's smaller than the diameter of a nucleus of an atom, built over the scale of an entire small town of 4 kilometers. There's 4 kilometers on each edge. So it's a very, very, very sensitive experiment. But knowing what we know about gravitational waves and about the sources, we expect that within the next few years, these detectors should be seeing multiple sources of bursts of waves per year. So it's an exciting time. That would mean that for the first time after a century, we could verify Einstein's equations as a theory, and we could also solve the equations that are needed to tell us what it is we're seeing. So that, and after a century of both of those activities going on, they've actually converged around the same time. So that's good. So another point, though, to make about this is that it will then allow us to figure out what's happening out there in the universe. If we understand through simulations what the signal should look like from a given source, so we'll be able to detect gravitational waves from colliding black holes or neutron stars, relics of the Big Bang, probably most importantly, things that we've never ever seen before, because we've never seen gravitational waves. So we can only think of certain kinds of things. Very likely we will see signals from things that we had never ever anticipated before, because it's a completely new source of information about the universe. So another point to bring out about this, though, is that this is a new era of science, because right now those simulations that I showed you are generating not just gigabytes, but actually terabytes of data, and soon to be petabytes of data. And we're doing experiments, and those laser gravitational wave detectors are generating ultimately petabytes of data. And so both of these have become very, very strongly data-intensive problems. Coming back to general relativity, this is something that's very new for that field. So going forward, just ahead, all I told you about so far is solving Einstein's equations. That's just one piece of the picture of astrophysics. It's just the gravity part. I didn't tell you this, but we didn't put any matter in any of those simulations. So there's no hydrodynamics, no magnetic fields. But the real world has those. So if we wanted to solve a real problem of, say, a gamma ray burst, we have to now find ways to integrate expertise in relativity, hydrodynamics, nuclear physics, radiation transport, etc. And so these are very different communities who basically don't even know each other, and we need to find ways to integrate them to look at this problem of the gamma ray burst. It also is going to be demanding scalable algorithms and complex simulation codes. If you were to add up, we know the equations that we have to integrate here. So we look at how complicated they are. We can work out how many arithmetic operations are needed in every time step in order to solve this problem. And you can show very easily that you have many petaflops of sustained computing in a week in order to do a very sort of simplified version of this calculation that has most of the physics in that you want. So it demands very, very intensive computing environments. So the main point then from all of this is that this field of general relativity and gravity is completely transformed. And after centuries of small science and small data, in just a few decades, we have factors of thousands per every few years that are changing. The collaborations are getting very large. These are global collaborations of hundreds and hundreds of scientists, and same on the theoretical side as well. Okay, so that's just the beginning. So I'm just getting warmed up for what's coming. So there's a new era of astronomy that people are very excited about, data-intensive but also transient-based astronomy. So most of astronomy, the history is you look through a telescope, then cameras were developed, you take a picture, and you go analyze it. But you typically could not actually catch something in the action of happening. But now we're going to be looking and actually catching in sort of real time what's happening out there in the universe. And so looking at events as they occur will be a new style of doing astronomy, and it's going to take people across the planet. So now this is your laboratory. You have people, and you have networks that are connecting them, and you have instruments. So you can think of them as sort of as sensors. So the kinds of sensors we have are radio telescopes. There's a thing called the Atacama Large Millimeter Array in the Atacama Desert in Chile. It's an array of about, well, right now, 16 detectors, 16 dishes. It'll soon be of order 50, and early scientists going on. This is $1 billion a radio telescope that has many international partners, so it's a very complex system. This is a picture of the Extended Very Large Array in New Mexico. So these are about to go into operation, and they will usher in a new era of radio astronomy. There's another project in Antarctica called IceCube. It's a cubic kilometer of ice that is now instrumented to look for neutrinos from cosmic sources. And so ultimately, if you see neutrinos coming from somewhere and you'd like to see, is there something in the radio, is there something in the optical, you want to be able to connect these together. So that's a cyber infrastructure nightmare because it's hard to get data from the South Pole. This is literally at the South Pole, and they're generating a fair amount of data that's usually shipped back on tapes at the moment. Optical telescopes. We have very large optical telescopes that are being proposed and planned now by numerous international communities. So I just show a couple of examples here, but they're much larger than current optical telescopes. So currently we have something like 8 to 10 meter class telescopes. That's about the largest that's really operating. We have things on the drawing boards that are up to 40 meters in diameter. So these will be much larger optical telescopes, and they will be in remote sites in Hawaii and Chile and so on. Now, there's a gravitational wave detection, which has up to now has never been a part of astronomy because it was really a physics experiment. But now the detectors are going to be sensitive enough that we'll be seeing routine events within a few years. And in fact, there's a plan that says we currently have, in the US, we operate 2 gravitational wave detectors. One of them will have 2 advanced detectors installed in the next couple of years. And it turns out we've realized now, if we move one of those detectors to Australia, if we could do that, then we would be able to tell not only that an event happened, but we'd be able to tell where on the sky it comes from. So gravitational wave detectors don't tell you where something comes from. They just sort of either vibrate or they don't. But if you have 3 of them, or maybe a network of them around the planet, then you can tell if something came from over there, first it hits this one, then this one, then this one. You can kind of triangulate and figure out what direction it's coming from on the sky. That would turn it into a telescope, which would make it absolutely relevant for a revolution in astronomy that I'm just warming up to here with all of these different activities. Then there's a thing that's called the LSST, which is the Large Synoptic Survey Telescope, which is also being planned, and in fact it was the top recommendation of the Decadal Survey in astronomy. And this is really exciting because it's a completely different kind of telescope that will survey the sky. And what it does is it points here and it takes a picture. It takes a 3 gigapixel picture. So 3 gigapixels. And then it moves 15 seconds later, it's taking another one. 15 seconds later, another one. And it does this all night, every night, and every 3 days it can survey the entire sky. So that's half the universe. It's able to see roughly half of the universe. And then it starts over again. So it's going to make a movie of half the universe, and it's going to generate a lot of data. So how much? If you're familiar with a thing called the Sloan Digital Sky Survey, that's in the last decade, the most advanced survey in astronomy. It generated 40 terabytes of data. This is going to generate that much data every night. So a decade's worth of astronomy now being compressed into every night. And it's going to be generating it on a mountaintop in Chile. So that's a data volume that is just unprecedented in astronomy. Now, or in almost any field, in fact. Now, we're going to, can you top this? Yes, we can top this. The Square Kilometer Array is a project that has got a worldwide set of partners behind it. It's on the drawing boards right now, but there are some early prototypes and so on. And so in the next decade or so, if money is found for this, it will be generating data at the level of exabytes. And depending on who you talk to, it's exabytes per some time period that whatever the technology allows, it will be that. So it can really saturate almost anything. And so we're talking about going up many orders of magnitude, millions and trillions of times more than what we're seeing now, but coming on a routine basis. That's going to drive all kinds of algorithm development, technology development, networking development, computing development, et cetera. So this is going to be an exascale computing problem just for the data analysis, not to speak of simulating the events that you might find. Now, what we'd really like to do is something happens, and you can imagine light bulbs going off all over the place, right? So something happens out there, all of this happens, and we want to then somehow correlate what we've just seen in LSST, what we've seen in gravitational waves and neutrinos in the radio and so on, and we want to do simulations at the same time. So we want to be notified, in fact, and in fact, some of you have phones like this. There's a transient astronomy application that will actually notify you now when an event has been detected. So you can imagine many astronomers and physicists, just waiting, and their phone suddenly rings. It says, aha, a gamma ray burst just went off. And you might want to then go do a simulation immediately with some kind of data that's then put into that. And then you want to then predict. If you look in 2 hours or in 5 hours, you may see something, but you better look there now in the radio. And so you see, it's really a data-intensive, immediate feedback problem that's really important for the future of astronomy, but something that's not done very much quite yet. So we have to then find a way to provide the computing environment that has this as its background. So this astronomy, future of astronomy is really driving every area of science and technology right now. I mean, particularly in the computational and data-intensive methods. So this is going to require integration across many disciplines, end-to-end activities. And all of these communities are going to be needed to look at this. And these are not, if you're not an astrophysicist, it may sound like they're all astronomers and they all know each other, but it's not true. These are very, very different kinds of communities that need to work together. So we need to find ways for them to share data, for them to share software environments, and their knowledge in real time. Okay. So I'll give you another example. It's not just these sort of singular heroic experiments that you might find, you say, in astronomy, okay, that's one field. But here's another example, Hurricane Katrina. So these are the actual locations of Hurricane Katrina as they were observed. And each one of these lines shows a computer model of where that hurricane would go according to that particular model. And this is 5 days out. This is about 4 days out. And around 3 days out from right about here, the models began to converge and we knew it was going to hit New Orleans. So what we'd really like to be able to do in this emergency forecast situation is to integrate observations from satellites with observations across the centers across the Gulf of Mexico, integrate those into models, dynamically determine which of the models is actually giving the correct path by looking at the observations. And so we ought to be able to much more quickly figure out where the hurricane would go. And then secondly, we have to couple models of the storm surge, because that's the thing that's really dangerous for people. When the hurricane's blowing water at 180 miles per hour with 180 mile per hour winds, it tends to get built up in the northeast part of the storm, and then it's driven by the hurricane. And so that's what happens when you have a big storm surge, something like, in this case, a 27-foot storm surge that hit the New Orleans, or particularly a little bit to the east in the Mississippi border there. That's the damaging part. But those are different communities. The people who do the storm surge modeling are not really the same as the ones who do the atmospheric modeling. They're not the same as the ones that do the satellite observations. But all of this needs to be integrated. And then you have the issue of how will people respond? Where should you put supplies? How should the roads be configured? So you want to have only outgoing roads and such things. Where should you put the buses and so on? So and what would be the economic impact? So this brings in the social, behavioral, and economic sciences. So the point is, this one problem, again, brings this integration of many different kinds of expertise. And you want to be able to do the integration of that in real time, because you've just got a few days. And so this, again, drives the same issues that I was talking about in astronomy. And when you look across all of science and engineering, you see this everywhere, these same kinds of things. So this is what I call grand challenge communities for complex problems, where it's not just bringing together a team of people or even a community, but you need to find ways that are at a higher level of abstraction so that people can work together that will never necessarily know each other, probably not know each other, so their knowledge has to be rapidly connected in some way. So it's about connecting people. This brings in the social networking technologies. And so there are many examples of this, but I'll give you an example of what some people are doing now to experiment with this. So the Cactus group, or there's a large collaboration of people doing computer simulations of black holes. They actually are using things like Twitter now, so their simulation codes can notify their collaborators if something interesting is happening in a simulation, or they can post their visualizations directly from the supercomputer to something like Flickr and say, I've got these beautiful pictures. These are my kids, and here are my precious black hole collisions. And so, but in real time, you can bring these communities together through these social technologies. So I think the social, behavioral, and economic sciences are going to be critical in helping us understand these issues of how these communities are going to be able to work together. So I'll just summarize this whole portion of my talk, which is the bulk of the science part of the talk, to say that scenarios like this are seen in all fields. So of course, there's a Large Hadron Collider. This is a little bit different in that you have all of this data coming from a single place on the planet, but then it gets redistributed across the whole planet. In fact, there are tens of thousands of scientists in a few dozen countries working together on this. They just did a warm-up run in the last year to sort of show that the machine is operating correctly. They reproduced the standard model of particle physics just in their warm-up run, and they generated 7 petabytes of data that has then been replicated and distributed across the planet. So 35 petabytes from this warm-up run for doing the next generation science in particle physics. Here's something that I really want to stress. This is to illustrate DNA sequencing. So it is now possible for any biologist with a grant from the NIH or the National Science Foundation to buy a machine that does DNA sequencing that can generate data at a rate of 1 terabyte per minute. And so this is really scary. So it's not just like we have to worry about the LHC. This is like an LHC worth of data in every single laboratory of a biologist. And so that's the kind of challenge that we're looking at. So what do you do with all this data, and what are the methods for doing this kind of science? So just to summarize, this is sort of my sort of changing science, changing the culture of science and methodologies. The kind of change that we're facing is really dramatic, and there are a lot of articles and, in fact, entire issues of magazines devoted to this. Most recently, Science magazine had an issue devoted to this just a few weeks ago on data-intensive methods, and you should put this down a little bit. And so when I first came to the National Science Foundation about 2.5 years ago, Wired magazine proclaimed in a very dramatic fashion that science is over, that it's no longer theory and experiment or even computation. It's just looking for trends in data, and so the methodologies are changing. So I think perhaps that's a bit over the top, but science isn't over, but the way science is being done is certainly changing a lot. And so sometimes, rather than saying science is over, people are saying it's a fourth paradigm of science. So the thing I'll leave you, the last thought is that we still think like this, because this is the way we've been trained for years. But the kind of radical change in just a few decades, the factors of 10 to the 9th and more, can't be adequately addressed with our current approach, which is typically incremental. So we have to really rethink how we're going to do this. I just want to, as a pep talk to students, although this is a bit scary, just imagine that you are 10 to the 9th times more powerful than your professors were when they were your age. So that's, you can do much better science. Okay, so that just sets up the problems that we have to face. So we have all of these crises to deal with. And when I came to NSF, the entire financial world collapsed, and we began to really worry, could we do anything given all the financial problems we're having? We have all these crises in computing, data, software, networks, etc. And so I'd say we're not on top of this, but we're beginning to recognize that we have a problem, and we're going to make investments in a different way. So I'll point out a couple of crises. The first one is just this plot that shows on the scale on the top right-hand corner here, the year on the lower axis, and then the number of processors in a logarithmic form. And a few years ago, you see that there's a kind of a really big change in the size of the machine. So we're now suddenly looking at machines that have hundreds of thousands of processors, perhaps millions, or processor cores, not the same as processors. But the point is that this means we have to think very hard about what is the programming model at this level. What are the fault tolerance techniques that you have to use? Imagine you all have a computer of some kind. Usually something fails on it. If you had 1 million components that were like that, something can be failing every hour, and you have to have then scientific instruments that are using these incredible computational methods on all these components, and something's failing all the time. So you have to really rethink the applications in this kind of space. Also, the next thing is, and I'll focus mostly on this going forward here, data provenance and visualization. How do we do this kind of science? And then software. I don't have time to go into this, but I'll just say that I think software, as really the modern language of science now, has to be taken much more seriously than ever before. And if you think about, as a physicist or a mathematician, of course, you have to have advanced calculus and many advanced mathematics courses, but you rarely have a course in software engineering, which is how you actually express all of this. And the only way people are going to work together effectively is if their software is compatible. And the only way we're going to be able to be sure that the science we're doing is right is if it's verifiable, right? So think about that. Many problems, and it's getting more complex as we go forward. So let me focus on data for a few minutes. This is a graph of the amount of data as a function of year, and this is the amount of data. So all of these lines are basically up and to the right. So it's logarithmic, huge amount of data is being generated, and it's been estimated that a few years ago, we crossed over a line where all the data that was ever generated in the history of humanity is generated, that amount of data, we're exceeding that in every year beyond that year. So that means we generate more data this year than we did in all of human history, and more than that in the next year. So it's really a phenomenal problem. There are many reports that say we have these crises in data, and we better think about it. So let me just not solve that crisis yet, but just point out these other issues that I think are really important for us as universities, as funding agencies, and so on, to recognize that we have to really deeply think about what are the organizational structures for multidisciplinary computational and data-intensive sciences. So there are these recommendations from a thing called the PITAC report from a few years ago, Presidential Information Technology Advisory Committee. Universities need to significantly change their organizational structures. I've been talking about that all morning. Berkeley clearly has been spending a lot of time thinking about this, is making a lot of advances, and has certainly got one of the most advanced ideas for how this could be done through many centers. For example, CITRIS seems to be really very fabulous activity. But then looking at other things like the federal agencies themselves, like the National Science Foundation, Department of Energy, we have to really rethink this. So I'm going to come to this in a minute, what we're trying to do about this. But then education. I think we have to really think about how to exploit this, not only exploit this for advantage in education, but to think about how should education actually be done. So we're still equipping high schools with labs that teach Newtonian physics from experiments done by Newton and Cavendish and people like that. Whereas perhaps we could be doing this in a different way, the way science is really being done now. And with the digital revolution, with electronic textbooks, you could imagine directly connecting in data sources from scientists around the world into the curriculum, and they could be actually brought right into your first grade textbook and really learn about how science is being done. Also, the excitement of science, I think, could be brought more directly into someone. If you could look at from your textbook and you see that's black holes colliding on a big supercomputer somewhere, or those are from a radio telescope, that would really excite people as well. All right. So we're trying to develop a national cyber infrastructure. This is from the National Science Foundation point of view, where we have these supercomputers, we have networks, we have campuses. Really important point here is that most of the scientists that we fund and that are doing the science are on university campuses, and many of the things they're using are remote. So there's supercomputers, telescopes, and all of these things. So how do we connect them? We have these very large supercomputers, for example, at the University of Illinois, the petascale supercomputing facility going into place in the next couple of years. We have DNA sequencers, of course, on campuses. So that's kind of the landscape. We have these large facilities, and then we have a student sitting here who doesn't think anymore about, oh, I just have to do some data thing, or I have to use a computer. But this is the environment they're working in. to say, I may need to look at all of these things in order to solve the problem that's of interest to me for my PhD thesis. So how do we educate people in this new environment? It's really a deep question. Another thing that we're very concerned about is, given the complexity of the environment, and I mentioned this a minute ago, how do we know that we could ever reproduce our science results if we had all of these activities and you're borrowing software and sharing data and doing computation, et cetera? How can we reproduce the results? How do we know that things are correct physically? Okay, so given all that, for the next few minutes I'll talk about some recommendations and then what NSF is planning to do about this. So we had a thing called the Advisory Committee for Cyberinfrastructure, and some of you in the room have been very helpful in putting in a lot of effort here. We created 6 task forces that covered all of these areas: Grand Challenge Science, high performance computing, software environments, et cetera. Campus bridging, how do we connect campuses to the national cyber infrastructure we're trying to put together. Many workshops, and I'll simply say, I won't go into the details of these for time, but one of the top recommendations, in fact, this is a resolution that I'll show you in a minute that was voted on by the ACCI unanimously, said a permanent programmatic set of activities in computational and data-enabled science. And they insisted on inserting the word data in there. So some of you have heard about CSE, computational science and engineering. The data word was inserted to make a statement that data is really different from traditional simulation, although they overlap somewhat. And so we need to think about these new ways of doing science based on all of the data. So we need to create permanent programs. So we are looking very hard at how we would establish a so-called CD/S&E program at NSF. So, in fact, this is in slightly more detail. It says, and this is the resolution, there's a one-page resolution that says the NSF should create a program in CD/S&E based in and coordinated by the Office of Cyber Infrastructure, but it should be collaborative with the relevant disciplinary programs. And so we're now working hard to figure out how we can implement something like this that every unit at the National Science Foundation participates in, and we cover all areas of science, from social and economics and so on to biology, physics, computer science. So we do cover every area of science. We need to find a way to integrate that, and so we're working on it. So what are the actions then? So we have the President's budget request for FY 2012. This is right now, as you know, in February, the President has a budget request. Congress then looks at that and says, I don't know. they'll think about it. But we have requested $7.8 billion. And we have two activities that cut across every single unit of NSF. So these are probably the flagship investments in FY12, which would be a thing called sustainability, or science, engineering, and education for sustainability. So how do we sustain life on the planet? And that means everything from renewable materials to electrical power to climate and environment to bio materials, for example, to new chemistry, green computing, all of those things. But at the fundamental level of the research, the basic physics and mathematics and so on that support that, as well as applications that might go all the way to industry. And the other one is a thing that I'm going to focus on called CIF21, Cyber Infrastructure Framework for 21st Century Science and Engineering. So this is very large. This is $998 million in the NSF budget request for FY12. This is about $117 million. So I'll go into just a little bit of detail about what we're trying to do with that. So this program would, if it's funded, develop money for every single unit in NSF. This builds on top of the investments we're already making. For example, there's a thing called the TerraGrid, some of you know, which has a lot of supercomputing centers that are integrated through this environment that is created. It's being replaced by a thing called Extreme Digital, which is a sort of a new version of that. And there are also investments in software infrastructure, a thing called SI squared, we call it, where we're going to actually be investing something that I hope will be in the order of a few $100 million over a decade in software, taking it as a first-class citizen in cyber infrastructure. So this CIF21 builds on top of these other investments that we're already making as sort of an integrating fabric across all of NSF. And it's going to have activity in these areas: community research networks, where we try to develop the abilities for teams or communities to work together that are doing computational and data-enabled science. Data-enabled science itself, I'll say more about that in a minute. New computational resources. This is at the research and development in the area of computing, simulations, using new technologies, GPUs, and so on. And then access and connections to resources. So how do we actually connect into these remote things that we're developing, building all around the world? So let me focus for a few minutes on science, the data-intensive science. So the one thrust area that I go into a little bit more depth here is this data-enabled science. And we're imagining these three tiers. The first one you could think of as data. Where do we put the data? How do we store it? What are the services that actually allow people to access it? So right now, we thought, in the history, we thought much more about computing, and the data has just been something you've sort of dealt with. But now we have to think about, this is really important because science is changing, so we need to really provide a way to provide a national data infrastructure. And so that's really where we're going with this. And secondly, what is the science of data? So this is at the level of information. How do you extract information out? What are the algorithms? What's the fundamental computer science and mathematics? How do we make decisions? How do we find features in all of this data? And the last part of it is, the third part, is data-intensive science itself. Data-intensive astronomy, as I mentioned already, physics, etc. So there are these three different components that we have in mind. So there are some very deep implications towards this sea of data that we're talking about. And I think I'll skip this and just come to the questions, because they really change when you think about data as the medium for doing science, and also the way we communicate science, or the way we share with our collaborators. We share it by exchanging data. Email, perhaps terabytes of data, perhaps exabytes of data in the future, and we'll have to be able to do that. So how do we remove the boundaries between these communities, and how do we incentivize sharing? That's a really critical problem, and we're thinking about, therefore, what do we do to move communities forward in this way? What are the policies we have to implement to make this possible? And how do we attribute credit for this? It's a new publication form, actually. So if you have a lot of data, that may be more important than your 4-page physical review letter that you propose or that you have published. And yet at the moment, it's not something you normally put on your CV. So how do you actually change the culture so that publications of data count, or software environments? And how would data be peer reviewed? And I mean, more generally, what is a publication anyway in this new way of doing science? So we're looking hard at this, and I'll point out 3 statements that I think everybody would agree with until you think a little bit harder about them. Publicly funded scientific data and publications should be available, and science benefits. Right? Who would argue with that? There has to be a place to put the data and a way to access it, and there has to be an affordable, sustainable cost model. These are getting increasingly loaded with questions, right? So, but the first question is, then even if people will agree to this statement, then they'll say, well, what data has to be made available? Is it the raw data? Is it everything I've ever collected? Is it just data that I've somehow massaged? Is it the data that I'm willing to give to people? Does it have to be peer reviewed? Over what period of time? Etc. So these are the questions that bog down the discussions for years, but this is where we're really taking very seriously now, recognizing that it's a necessity now. And where do you place it? Should it be on the author website? So 15 years ago, that was pretty cool. You would put your little scientific code up on a website and somebody would download it, and that's sort of data curation. But now that's simply not good enough anymore. We have to really think about where it should go. It's clear to us that libraries will be much more central to this in the future than they are now, because they are the curators of knowledge, and knowledge is going to be increasingly in digital form in the future. Who pays? This gets to be a real problem. This is really going to cost money. Certainly the NSF will have to pay for some of this. Certainly institutions like Berkeley will have to pay for some of this. But no one's really sure where the boundaries are, or in fact what the cost models are right now. So we're looking very hard at this. The National Science Board is looking at this. How long do you make it available? You'd really like to have some data that Newton actually collected, probably, right? And we do have notebooks, but you'd like to have some data that was collected by a particle physics experiment from the 1980s. Probably you can't get that anymore, or even if it had been made available, it wouldn't be in readable form, probably. And how do we enforce this curation of data beyond, say, a 3-year grant? After the grant is over, who pays for it then? So these are pretty hard questions. So there's a lot of variability in the requirements across all the science communities. That's clear. Some have really strong cultures of sharing data, others don't. So we have, as of 2 months ago, we now have a requirement. If anyone writes a proposal to the National Science Foundation, you have to provide a data management plan. You cannot submit a proposal without a data management plan. But at the moment, except in special cases, we don't tell you what it has to say. It doesn't say that you have to share the data with your worst collaborators or your worst competitors or anything like that yet. But it will make you think about it, and it will be peer reviewed. So your community will look at that and see if that's reasonable. And then we will begin to collect data on this and begin to tighten up policies as we see really where the trends are. But at the moment, we're not going so far as to require anything very specific except a data management plan, which could say, I don't really need a data management plan. But then your community will be looking at that and say, well, maybe you do. So this means that we have these changes coming to policy. This is currently NSF policy on data. It's been around for a long time. It says that you're expected to do the right kinds of things, but it doesn't really require you to do it. And so now we're requiring you to have a plan, and I'm just saying that this is going to be really important for the future of science, and we're looking hard at what that will actually say in the future. But right now, we haven't gone beyond this. So let me just conclude here then. There's a lot more that I could have gone into, but if there's time for questions, I'm happy to talk about them as much as you have time for. I think the first point, I hope I made it abundantly clear that science and society are profoundly changing in these new ways of doing science with the computing revolution, et cetera. We see it in social behavior already. We see what's happening in the Middle East, largely aided by technologies that no one had heard of just a few years ago, for example. Really huge changes. It's amazingly rapid. And so also we're looking at problems now that cannot be addressed typically by any individual scientist or community because the knowledge base is not there. They're too complicated. So we need to find ways to address all of these elements in order to solve single complex problems. And then ultimately, I just think we have to think very hard about what's the future of a funding agency or a university given all of these changes. And I invite you to help us think that through. So I'll conclude there. Thanks.
Thank you very much, Ed. We've got time for some questions. Please use the microphone for the questions so we can have the people in the distance audience hear the questions. Here, and then back there.
Thanks very much for a really interesting talk. You mentioned briefly making software a first-class citizen. Could you say a little bit more about what that means?
Sure. So there are many aspects to it. I mean, typically software wasn't ever even explicitly funded by the agencies. It was something that a professor would have a graduate student do. And that's just, it's a recognition that that's not adequate anymore. So I spent most of my career learning that part was probably the hardest part of solving Einstein's equations, was understanding how to develop the computational techniques and how to put that in a software environment that allowed me to get correct results, and particularly in working with collaborators. So that's, first of all, it's a recognition of that. Secondly, it's a recognition that it will cost money at the level of what supercomputers cost. And so a supercomputer might cost $30 million. That's typical NSF size for a medium-sized supercomputer now. And so we will be investing similar amounts of money annually in the software environments alone, and that'll be increasing. So I think right now the balance is pretty far off in terms of hardware versus software, and we're trying to correct that without doing damage to the needs for the computing hardware itself. So of course we have to make those investments too. So we're trying to grow the other areas a lot. And I think it also means taking it seriously, so working with universities to get a scientific training so that scientific software development is actually part of the curriculum and part of the culture where it's expected, and its challenges are recognized as really intellectual challenges as well. It's not just a matter of training people to write Fortran code. It's much deeper than that. So it means all of that.
I also want to compliment you on that talk. I thought it was terrific. There's a question that you danced around, and that is what these changes to do to what we think of as the scientific method. You did mention reproducibility. Is reproducibility really the right metric to use? If I can refine the Katrina simulation so that they really track what happens with the storm, do I need to save the observational data anymore, or is the simulation then the preservation. So what are your thoughts on that?
I think, okay, it's not, in some cases it is exact reproducibility depending on the circumstance. And right now I would say that's virtually impossible given the way we publish results. All right, so even in the simplest cases it's not really possible, and sometimes it is, but quite often it's not in a strict digital sense. So if you want ultimately for people to begin to trust people's results that were generated somehow through data analysis or computing, you'd like them to be able to actually see the steps that you took in order to get them, as you would require of a theorem, for example. And so we're not at that level yet, so that's part of it. But I do agree that it's not necessarily the case that ultimately we want every single aspect of a very complex thing to be reproduced at the level of 64 bits of precision, because that's just not going to be practical or maybe not even necessary. So, but that's something that I think the community is going to have to kind of develop over time. But I think they're only really beginning in a broad sense to take this notion really seriously. And so we're beginning to work, for example, with journals. So Elsevier has got a new journal of computational science, and they just had a contest they call the Executable Papers Challenge. So if you wanted to submit a result there, that was computational, then we'd like to make that sort of an executable paper so that someone else could actually take it and actually execute that paper and get all the the input stacks, the software, and figure out how to do that in a way that allows others to do it. So these are kind of beginning steps towards that.
So you mentioned data sharing.
Up there.
So I was wondering what you think about the interaction between data sharing and privacy concerns, particularly for biological or medical data.
Right. Okay, so those are clearly special cases, of which there are a lot, in terms of anything that has to do with data about actual people, whether it's sociological or medical data. So that wouldn't ever be required to be shared, except potentially in some anonymized way. So there are people that sometimes that kind of thing happens. Although it's also been shown that anonymized data is not that anonymous. People have shown that you can actually figure out who people are by clever analysis and so on. So we're talking more about the kind of things where we simply need to be able to encourage these kind of collaborations to take place by providing open data sharing software and so on.
You've shown how the hardware to do cutting-edge research is a truly international collaboration now, requires international financing, essentially. They would then stand to reason that some of these computational challenges when it comes to education might also be solved in an international way. I wonder if you could speak to what other national or pan-global science foundations are thinking about in terms of solving these problems at the educational level.
At the educational level, you mean in terms of sharing?
No, I mean in getting students trained to do this computational thinking and getting them ready and prepared for this 21st century way of doing science.
Right. So we do have discussion with other funding agencies, most closely probably with the European Commission on this particular area. And so there have been proposals. In fact, there's a proposal out of Amsterdam. Peter Sloat talks about an international master's degree in computational science. And the idea would be to find some way to create at least core elements of a curriculum that would be needed, that would be sort of accepted by, well, the trouble with it is that different communities will have different sort of needs for this. But nonetheless, there are attempts to do this. And we've talked about also developing joint funding actions where you could send students or to workshops that are carried out internationally, or to have curriculum development conferences done jointly and so on. So we're having those kinds of discussions. I would say we haven't gotten very far with it, though.
Great. Great talk. So my question is, I'm a software engineer, and I know a lot of people who are very good software engineers. The really good software engineers tend to leave computer science departments, not even get degrees, because it's the computer science department, not a computer computational artistry department. And what we've agreed upon after many years of consideration of what's really flawed about computer science departments is that we don't have the equivalent of an art school. It's really, engineering is really an art, not a science, and it has a certain artistic method to it, which the academia is almost antithetical to, rather than supportive of. And there is computer science that's valuable, and theories of incompleteness and undecidability are helpful, but they're not at the heart of the matter of writing software. And we have schools for if you want to be a singer, or if you want to be a surgeon in another form of artistry, or if you want to be a visual artist. What we don't have is any place where you can go and learn the art of software artistry, the people you critically depend upon eventually to write code, and to actually teach that. Everyone ends up teaching themselves who's really, really good. And they all have to start when they're teenagers in order to do it. It takes years, and there's like zero recognition of this in computer science departments, and it's extraordinarily frustrating and maddening for software engineers. So I say what you need, and I'd like to hear your remarks. Sorry to make a speech, guys, this question. But you need a Department of Computational Artistry, and there's zero conversation about this. What do you think? Think it's crazy? Or anyway, we could get this to happen?
No, I think you're frustrated for good reason. I think most people in this audience probably appreciate at least some of the things you said. Certainly the core of what you said is that software engineering, as it's typically taught, is not supporting either the kind of things that are needed in perhaps in industry, but certainly not in scientific computation. And I think the curriculum has to be really deeply rethought. And we had a lot of discussions this morning about this, so at least here at Berkeley I found great resonance in these ideas. And I think it needs to be done, needs to be taken seriously in every department, as well as having some kind of a, perhaps done through a center for computation or a school of computation. Or, for example, here at Berkeley you have the national labs that have been living and breathing and leading this entire activity for decades. And so providing perhaps a better integration between what's the knowledge that's there and with the academic community would be really important.
Well, Ed, unfortunately our time is up. Thank you very much. We appreciate it. You're about halfway through your gauntlet we have for you for today. If you want to catch Ed now briefly, we might have to migrate to the outside area. But Ed has a few minutes to stick around for one-on-one conversations. Thank you very much.